Welcome back to our IB Physics video series. This is the third and final video in IB Physics Topic 7, Atomic, Nuclear and Particle Physics, where we will be looking at the Standard Model, bosons, leptons, quarks, hadrons and Feynman diagrams. At this point you may have believed that protons and neutrons were the smallest particles possible. However, this is not true. Protons and neutrons are composed of smaller particles described by the Standard Model. The Standard Model states that all matter is composed of 6 types of quarks and 6 types of leptons, and all fundamental forces are mediated by bosons. Simply put, quarks are particles that compose heavier atomic particles, leptons are independent particles that mostly transfer charge, and bosons are tiny force particles. But how do these all interact with one another? The Standard Model divides matter into 2 categories: elementary particles, the simplest particles in existence, and composite particles, particles composed of multiple elementary particles. Let's start with elementary particles. These are commonly categorized as either bosons or fermions. Note, fermions are further subdivided into leptons and quarks. The composite particles are hadrons, nuclei, atoms, molecules and ions. We've already covered nuclei, atoms, molecules and ions, however hadrons are new. These, nicknamed heavy particles, are divided into baryons and mesons. Baryons are composed of 3 quarks, or antiquarks, whilst mesons are composed of 1 quark and 1 antiquark. But what is an antiquark? Well, all quantum particles can be defined by certain quantum numbers. These are their properties, including charge, spin, charm, strangeness, lepton number, baryon number, and colour. During the Big Bang, all matter also formed antimatter. This is matter with an identical mass but opposite quantum numbers. Antiparticles are written with a line above them, or with an apostrophe. So, bringing this together, the antiparticle of a proton is an antiproton, written as P with a line or an apostrophe, and has the same mass but a negative charge and opposite baryon number. So now that you know the basics of the Standard Model, let's cover some more detail about each of these particle groups, starting with bosons. As previously mentioned, bosons are particles that mediate the fundamental forces. The main bosons are known as gauge bosons. As a rule of thumb, the larger the boson, the smaller its force range and the shorter its lifespan. There are 4 types you need to be aware of: gluons, W and Z, photons and gravitons. Let's cover each one now. Gluons are massless particles that mediate the strong nuclear force experienced by themselves and quarks. Each gluon has a colour charge and an anti-colour charge, which is often visualized as a vector, up to a total of 8 possible gluons. Red, anti-blue, red, anti-green, blue, anti-green, blue, anti-red, green, anti-blue, green, anti-red, colour neutral, and anti-colour neutral. W-, W+, and Z0 bosons mediate the weak nuclear force experienced by quarks and leptons. Photons mediate the electromagnetic force experienced by charged particles, and gravitons mediate the gravitational force experienced by all particles. It is important to note that all bosons are an exception in that they are their own antiparticles, i.e. the antiparticle of a photon is a photon. The exception to this exception is W-, whose antiparticle is W+. Whilst there are other bosons, the ones focused on by the IB is the Higgs boson. This is a massive boson that is theorized to give all matter mass, first proposed in 1964. However, it was not until 2013 before it was physically discovered in the Large Hadron Collider at CERN. So, that's the basics on bosons. Let's move on to fermions, who interact with the forces produced by bosons. As mentioned before, there are 2 types of fermions, leptons and quarks. Let's start with leptons. Leptons are fermions that interact via the weak nuclear and electromagnetic forces. Every lepton has a lepton number of 1, and there are 3 types of charged leptons and 3 types of neutral leptons. The 3 types of charged leptons, each with a charge of -1, are electrons, muons, and tau. Then the three types of neutral leptons, i.e. with a charge of 0, are electron neutrinos, muon neutrinos, and tau neutrinos. Since every lepton has a lepton number of 1, every anti-lepton has a number of -1. The three types of charged anti-leptons, each with a charge of +1, are anti-electrons, also called positrons, anti-muons, and anti-tau. Then the three types of neutral anti-leptons, each with a charge of 0, are anti-electron neutrinos, anti-muon neutrinos, and tau neutrinos. Note that every lepton follows the law of conservation of lepton number, i.e. the lepton number stays the same during every interaction. This means that whenever a lepton is produced, an anti-lepton must be produced to conserve lepton number. For example, remember the beta decay equation, where a neutron converts into a proton and emits an electron and an antineutrino. So, on the left side, there is only a neutron, which has no lepton number and a neutral charge. When it becomes a proton, the charge on the right-hand side becomes +1. This is balanced out by the electron's -1 charge. But the electron carries a lepton number of 1. As such, an antineutrino with a lepton number of -1 and a charge of 0 is also emitted to conserve lepton number during the decay. With leptons covered, let's look at the next Fermion group, quarks. You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.